Wait, but who else is Bianca? Hopefully she's not saying Anyway, KJ, Claire, Bianca, anyone else who's coming back over the videos again? Hi. But wait, irreducible. I thought quadratics we always factored down. So when would we not be able to factor? Wait, quadratics are sometimes not factorable?
Yes. Well, they have no solution.
Algebra 1! They all tie together. Algebra 1, what are they talking about?
No solution.
Quadratic formula sometimes has no solution when the square root is of what type of number?
Quadratic formula.
Negative, when you have the discriminant that's negative. Because do all quadratics hit the x-axis? Wait a minute, why am I talking about the x-axis? Because the solutions to a factor are the x-intercepts. So if a quadratic doesn't have to hit the x-axis, there don't have to be solutions. If there don't have to be solutions, well, it's possible. It's not factorable. Ooh. If it's not factorable, then we're stuck, and we can't make it go down to look like, remember yesterday? Wasn't there a nice trick whenever we can factor down to be nice factors?
Yeah, some weird dude's name.
The thumb.
Oliver Heaviside.
Yeah, they was.
Heaviside.
That was so yesterday's joke. Anyway.
It's not that funny.
You're not that funny.
The thumb trick, the cover-up method, right? But it only works when we have the nice little factors, and we just mentioned not all factors are nice, or not all quadratics and other higher order polynomials can be factored. Hence the dilemma, and hence why we can't just have the trick. But what's going on down here is that, okay, if we can, we're going to go down to those nice little linear factors. Linear factors are the dudes that just have x to the first power. Wait a minute, they can be raised to squareds and cubes and fourths and, Guess what? The trick doesn't work if I have something like a factor that's squared or cubed either. That's a bummer. And then we have those weird quadratic guys that might not break down. What I need you guys to see, Jaden, because you were asking what to write down, right? That's kind of what I'm addressing. If we have linear factors, we're going to put things up top, unknowns that we're going to solve for, like A and B and C. They put A1, A2, A3. I'll probably just use A and B and C to make it easier. But if we have one of those quadratic guys that cannot factor anymore, quadratic formula gets us like imaginary numbers, we're going to instead put, or need to put into the numerator, an x term and a constant. Not just a constant, but an x term and a constant. The reason why, if you care, and if it would help, the reason why we need an x term and a constant is because up here, in proper fractions, remember the numerator can be greater than or equal to and can be broken down into simpler pieces. If the numerator can be greater than or equal to, then basically, if I've already dealt with the improper and I only have proper left, I need to make sure that I have the highest possible degree in the numerator for it to still be proper. So like a linear, okay, well what's 1 degree less than a linear? A constant, okay. But what's 1 degree less than a quadratic? A linear. Well, x to the first power. It doesn't really matter if there are two terms or not. But the idea is the degree. So a quadratic is an x squared. What's 1 less than that? A linear, or an x to the first power. So I have to have both a constant and a linear term. Or I should say a constant and an x term. Because I have to make sure I'm allowing for the biggest possible numerator, I guess, is one way of saying it. It can't be any higher. It can't be a quadratic, or else it would have been tied and I should have divided. It can't be linear, like an x term, because then it's going to be tied. I should have divided. Anyway, Jane, did you get the main points that you needed?
Yes.
Now it's highlighted. Now it's highlighted stuff. Anybody else still going? You guys want to grab a quick picture? Or are we good?
Actually.
Yeah, that's fine. Grab a quick picture if you guys want. Because as soon as I go to the next page, this will be too small for us to see, even if I dual screen it or dual print it. I'm just recording now. Just chuckling over there. All right, here we go. This is my summary, but hold on. Can we just do an example first? Let's do an example. Wait a minute. This is the example. Hold on. We learned how to do this with a thumb trick. I'm going to do an example first. Of course you don't get it. We haven't done it yet. So let's do an example all together. Then let me go back and show you the short, sweet version of my steps. Caitlin's in. Are you guys in too?
Sure.
She's giving me a thumbs up. You guys just stare.
No.
Anyway, come back.
Ready?
Ready?
Is everyone ready?
What's this first step of what you guys wrote down from the chart that I just took off the screen? Okay, how do I know if it's improper? What's the degree of the bottom? What's the degree of the top? Is the top greater than or equal to the bottom?
No.
Not improper, so forget that step. Go to step 2. Factor. Sweet. I like factoring. Do you? Let's go ahead. I wish. We already know what these factors are because we talked about them enough yesterday. X minus 3 times x plus 2. Now, once we have the factors, what's step number 3 say?
Linear.
Go back to step number 2. What are we supposed to do with the factors?
Oh.
Somewhere there's form. Does anybody see the form?
No. Plus 2 to the m.
We're supposed to factor the denominator. Oh, I see.
Oh, I thought we were.
I'm in my steps and not in these steps. Okay, it says linear or quadratic. Like, look and see which one you have. Which one do we have? Do we have little quadratics down there or little linears? Little linears, little mx plus b's. We have little linear, x to the first powers. So what do? Okay, hold on. We put together a sum of fractions. That's what's going on. Whether quadratic or linear, you guys missed like the verb of what actually is going on in steps 3 and or 4. We're forming fractions, we're forming partial fractions. So, coming back here, we'll come back to mine in a second. We're going to take that x plus 7 in its factored form, which is going to be x minus 3 all over x plus 2. We're going to form our fractions for each factor. So we have one factor, x minus 3. Another factor, x plus 2. And if you didn't know the thumb trick, and if we hadn't used this as an example at the beginning of class saying, hey, can you make the second side look like the first side? You wouldn't know what's up here. So we would just have to say, I don't know, and I don't know. Like in all of math, if we have unknowns, we throw variables in there and then think about what we can actually do to solve. Oh, hi, he bounced. I know. Now, from all of our solving this year, if we need to try to get stuff alone and we see division, have you guys gotten this yet? If you don't know exactly the path forward to like the final solution, can you at least tell me what you think I would tell you to do to at least like go one more step?
Something really complicated.
Nah, not complicated. No, I can't do that because they all have different denominators. I wish I could just say a plus b is x plus 7, but I can't.
Oh.
I could try to get the same denominator.
Wait, I would wait to try to find the A and B.
Yeah.
What about the thing that you showed us yesterday?
Okay, I know, but that one sometimes works. So I'm trying to tell you like the big process, and then the trick is cool. We can always have it at the back.
Oh, wait, no.
Try and subtract some stuff on the other side.
What makes this complicated besides all the variables? Try to ignore the a and b and x for a second. What makes it complicated? What operation?
Everything's in fractions.
Everything's in fractions. And how do we make fractions easier?
Multiply.
That's what I was looking for. Now, should I multiply everything by x plus 2? Would that make everything easier?
You know what? Oh my god.
It would make this easier, and it would make this easier. But, if I multiply everything by x minus 3, will that make everything easier?
You have to multiply by both of them.
I have to multiply by them both. I'm going to multiply, if you were trying to get rid of fractions in like 7-1, 7-2, substitution, elimination, review, wouldn't you want to get rid of all the fractions? How to get rid of all the fractions? I multiply by all the denominators. So the process, technically, to mathematically solving, we're kind of out of the partial fraction bit, and we're just in like, I don't know, how do we use our math skills to get A and B? Well, Alec was totally right in that there's division. So let's get rid of it with multiplication. And let's get rid of it by multiplying everybody by, well, the whole denominator, x minus 3 times x plus 2. Now, could you have gotten common denominators and then multiplied? Yeah, you could have. You could have. When I multiply, don't I need to distribute that to everything on both sides, keeping everything balanced? Chem kids, you can appreciate the balancing. Okay. Some of you might be able to shortcut this process and only write it once and then think of distributing it to all. But yeah, that's not stress out some of the other ones. It's easier to write it all down. Is this guy totally gone? The answer is yes. But what about this one with the a over x minus 3? What remains?
X.
You see it? How about what remains for the b?
X minus 3.
Okay, so let's write what we have left, yeah? On the left-hand side, we have x plus 7 equals, and you guys already told me we have an x plus 2 that remains with the a coefficient, and then we have, now a lot of you would have seen this at the beginning, and you would have been like, it's impossible to solve, because we have too many variables. But once upon a time, we had too many variables, and it was still impossible to solve. Not in chapter 7 yet. But instead it would have been something to do with complex numbers. If I was to give you something like a plus 2bi is equal to 3 minus 1i. What if I asked you to solve for a and b? This was like a long time ago. A lot of you thought it was impossible. You're like, 2 unknowns, 1 equation. But what made the difference?
Z equals A.
I's are different than A's. In complex numbers, what's this part? Real or imaginary?
Real.
Mm-hmm. And what's this part?
Imaginary.
So if they're separate, do I really just have one equation? How were we able to take that expression and make 2 equations? Purple equals purple and yellow equals yellow. It's one equation, but that one equation has different types of terms to where imaginary can only come from imaginary, real could have only come from real, so really, we were able to make a system of equations. Now how does that apply to what we're doing here?
The exact same thing, except the X and the A and the B and the
X is one type of term,
yeah.
and the 7 is another type of term. And the X could have only come from X terms, and the 7 could have only come from constant terms. Well, wait a minute, they're A's and B's, it's messy. Let's make it not so messy. If we were to distribute ax plus 2a plus bx minus 3b, guys, wouldn't the x terms have combined, right? And wouldn't the constant terms also combine? So we're grouping them by type. We're grouping them by type, just like we did with complex numbers way back when. Yeah, so what are you seeing? Ooh. How did Ella get 1? ax plus bx has to be how many x's? Okay, so if it's a little too complicated, hold on. If that was too much, then just say ax plus bx is 1x and divide everything by x. Think about it. If that was 5x, this would need to be negative 4x, right? If this was 2x, that would need to be negative 1x. If this was negative 3x, that would need to be 4x. I know whatever the a is has to add to whatever the b is to make the 1. Because the next term had to come from x terms, right?
Wait.
Oh, cool.
Now, Alec, maybe this one's a little bit easier. Do you see that 2a doesn't have an x and 3b doesn't have an x? So these two numbers must have made the number 7. Yellow plus yellow equals yellow.
Yes.
And purple plus purple has to equal purple.
Uh-huh.
Which is great, except I don't want the x's, they're in my way. I just want a's and b's to solve my system of equations.
Can you go over that? Like, I guess.
I have x terms, which are separate from constant terms. And these two don't combine because they're not like terms. Well, in similar logic, my x terms would have been able, or would have, combined to make that x term, and my non-x's would have combined to make that non-x term.
How does 2a minus 3b get 7?
They're all non-x terms.
But like, there's no.
But how do you figure it out?
You have to see
Just
who
say
has
7.
x's. They'll combine to make the x term.
But is that the answer?
Oh, well, I mean, I need to find
Can
A
you
and
drop
B.
the X?
Yeah, that's what I'm saying.
But can't I drop the X's because they all have one?
Yeah.
So that's why Ella was like, oh, hey, A plus B is 1 because AX plus BX is 1X. So whatever the A number was plus whatever the B number is makes the 1X at the end. Another way of saying it is that you could have taken from this, I could have factored out that common X. I could have divided X on the other side. Like, we could show work to get A plus B is equal to 1. Or you can just be like, oh, hey, it's the X coefficient plus the X coefficient is the X coefficient. And you can actually put that in words if that would help. Because sometimes the words of the process are a little bit easier for some of you than the actual math of the process. So then check it. Sophia, I'm coming right back to what you're thinking, I think. But can I first of all just be like, hey, for those of you for whom this helps, that came from the X terms, the purple, right? And this one came from the constant terms, the yellow. True? Yellow minus yellow, well, plus negative yellow equals yellow, and then purple plus purple equals purple. So don't we now just have a system of equations? And you guys can choose whatever method you want, from 7-1, 7-2, or 7-3. Do you want to do a stair step? Do you want to do elimination, or do you want to do substitution?
Eliminate.
Yeah, totally. Multiply that bottom guy by 3, yeah? So I'm going to get my 3a plus 3b equals 3. And a quick elimination is going to go ahead and give me 5a equals 10. Just like the thumb trick showed me yesterday, and some of you guys are like, let's just do that. Remember, it's only sometimes legal. It's only sometimes illegal.
Wait. No, you just skip all the actual stuff.
Well, I added down. Is that good? 7 plus 3 is 10. Then divide by 5. A is 2. And once we have A, we can come back up here and say, oh, that's right. A plus B equals 1. So B equals negative 1. And so at the end of the day, I can come back and take another look at my problem and say, zooming out, oh yeah, that's right. A was the coefficient on top of the x minus 3 rational function. B was the numerator of the x plus 2 rational function. So we're totally done with, hey, check it. 2 over x minus 3 minus 1 over x plus 2.
Okay, now it makes sense. I just got here.
Now, Jaden, hold on. Thumb trick. Let's review and make sure we know how to do it. Because if it works, it's easy, right? The thumb trick said, remember, coming back to the very beginning, the cover-up method said, whenever you have linear factors, the nice, neat, easy factors, I cover and I plug in what?
You plug in negative 2.
Nope. The one I'm covering, right?
3.
3. So then I plug in 3 to the remaining x spots. So what's 3 plus 7?
10.
And what's 3 plus 2?
5.
Guess what you're doing when you do the cover-up method? You're literally doing all this work of multiplying, seeing what's left, and then basically when you plug in 3, that's a 0. 3, that's times A. 3, that's the numerator, that's the other denominator, and dividing it. We're basically doing the entire process in one little cover when the factors are non-repeating linears. And so then we would do the same thing, covering up the x plus 2, plugging in a negative 2. Ultimately, a negative 2 makes that a 0. A negative 2 is a negative 5. A negative 2 is a 5. Same thing that would have happened in plugging in here. This whole entire process gets done.
So, why do you use the thumb thing? Because this entire thing is way much more like chaotic and it's a lot more
Here's the problem. This whole thing is the process that you can do for any function, regardless of what type of factors. The thumb trick only works when they're nice, neat little baby, non-repeating, both to the first power, linear, no squares. See it? So what I just said basically says sometimes there's ones where we have repeating, raised to powers, or squares. This method will work. So then can we go ahead and see my quick recap? You have that huge table with all the different highlights. But here's the long story short. What's wrong? I'm sorry, we're in math though. I mean pre-cal, but pre-cal is math right now.
Oh yeah, for sure.
Okay, so I need you guys to go ahead and accentuate this whole little, like, an improper fraction is greater than or equal to. When the numerator's degree is greater than or equal to, That's when we're doing what we showed on the other side, putting our numerator and our denominator, looking for some sort of polynomial plus some sort of remainder, which could have an x actually. We're rewriting it, we're simplifying, we're breaking down. Then we're factoring the denominator completely. If we've been able to do an improper fraction, then we're taking whatever is left and we're using that. Otherwise, we're just using what we were given. And we're splitting him up into, for linear factors, we're going to do like an A and a B and a C, I don't know, however many we need, over each and every linear factor, whatever it may be. And here's the problem. I don't really know, so I'm just going to put, I don't know, whoever your factor is and whoever your factor is. They're linear. And if we were to have something like an x minus a squared, we could actually, that gets tricky. I'll just leave that big old table for you guys to look at that. And we'll get an example then. But if we were to have like a squared by one of these, we would actually have to build up. But for quadratic, if that little leftover piece, or maybe the original function, if he's proper and not improper, if he has one of those quadratic dudes, I do like starting with B, just so it's different and it stands out, kind of like the book does. If we have any weird quadratics, I don't know what kind of weird quadratics. You might have one of these that can't factor. You might even have one of these that can't factor. Then it looks a little bit different what we put up top. And you guys just realized we just had an A and had a B, so we were able to say X terms, constant terms, purple, yellow, done. But if we had one of these, we might have like one of those and a couple of those, or we might have a couple of those and a couple of those. All of a sudden, what was just a two equation system of equations might become a 4 equation system. Ugh. That's why it's in chapter 7, because we need systems to solve the tricky ones or the harder ones. And even the thumb trick is a system. It's just a shortcut of it. Okay, so.
How can we step greater and negative A, negative B?
Because remember when we do factors, like in synthetic division, we put the 0 or the solution, and what's inside is an x minus. I'm just reminding you of the opposite sign, right? Oh, yeah. But you're right, it could be x plus, and then a would be a negative number, but what else? Okay, so this is kind of taking that huge old chart from the book and basically breaking it down into at least a short, sweet step 1, 2, 3. And if you guys notice, 3 and 4 are basically the exact same step of form the partials, but linear looks one way, quadratics look another way. And we could have even irreducible cubics, but that's getting a bit harder than we're probably going to see. Thumb trick, I think we've practiced that enough since I started that yesterday. Let me just leave that in there. Let me just leave that in there. Let me just leave that in there for us to come back to tomorrow. Okay, deep breath. Yep. Let it out. I want you guys to prove to me that you at least know how to divide. Divide? Why are we dividing?
I forgot.
Okay, ready, set, polynomial division, go. Hey, start in your groups. Be like, all right, guys, who goes in the box? Who goes in the box? Who goes in the box? The division.
Oh, the division box.
Because why are we dividing?
To get rid of what we don't want.
Yeah, basically, it's improper. And if we divide, everything is going to be a little bit simpler.
The denominator goes in the outside of the box, guys.
Good. I would pull up the UCF first.
Yeah.
And then I would factor my
Like if we took x on the bottom, would we have to divide it twice?
Oh, don't. You can pull out an x on the bottom, but if you do, there's no x you can pull out at the top, so it didn't really help you. So I would just divide the way it is. Jake, how's that division going? Alex, how's it going?
I just wrote the problem down. I want to see how it goes.
Those of you that are helping each other, perfect. Those of you that are not, I'm guessing you're already stuck, so I'm starting. Those of you helping each other, perfect. Keep going. Those of you that are not, I'm guessing we're already stuck.
Misty, what's the reason behind feeling tired?
This is a much deeper question that sadly will not help us.
I wanted to kill the CEO's
Although, I don't know about you, but warmth and having food in my stomach both make me extremely tired.
Both of those make you tired?
Yep.
Oh, I'm stuck. Where'd I go?
Well, and a lack of sleep, obviously. And when my iron levels are low, I get really tired then too.
When do you get iron from?
What do you stay for, bro?
Very like deep green veggies like spinach or quinoa. So that's like iron enriched, I think. Or fish.
Broccoli having?
Broccoli has some. I mean, it's deep green.
Good meat has it.
Cooking in a cast iron skillet.
How do you do that?
Yeah.
That's pretty.
Just don't do like tomato stuff in the cast iron. That's a bad idea.
Cheese.
The acid will melt the pan.
Won't melt the pan. It'll just
Damage it.
yeah. Think of acid. Huh?
Cheesecake.
How you guys doing? Did you guys distribute your subtraction?
Yes.
Because those cancel. Those cancel. Ooh, did you get 5?
Yeah.
X squared because you distributed that subtraction.
Cheese.
How do you go from there though?
Why? Why can't you? I've now gotten to a proper fraction. X cubed can't go into something that's lower than. It can if it was Alakine. It can if it's equal to. But if it's lower than, I can't. And so if that's true, well guys, what do you do with any remainder?
Put it over there.
Yeah. What was the point of all this?
To get rid of.
What we don't want.
To get rid of as much as we can. What were we able to get rid of? A y equals x. Pause. Is this fraction simpler than that fraction? Yes. That was a 4th degree polynomial on top. This is a squared. That was improper. I had to pull out some whole polynomials just to even get my fractional, my proper fraction to even break apart. I don't want to go breaking apart improper. No, thank you.
No, thank you.
That 4th degree is not going to help us. But that square, that quadratic on top is good. Jaden, how'd that division go?
Cheese quesadilla.
Now, I need you guys to realize something. This original function, the one I'm trying to break down, is technically right down here below, which includes x and plus. But do you see how there is a fraction remaining?
Yay.
That's what I'm going to break down. I don't need to break down this. It's already there. That's a part of my solution. I'm going to take this remainder, which is what I wrote down a second ago. Take the remainder, and that is the guy I'm trying to break down. So, let's check it. Emily, you already thought about pulling out that x. What did you get when you pulled it out? Does that factor?
Yeah,
X plus 1 times x plus 1, which is x plus 1. Oh, there's a square. Jaden, I'm so sorry. If there's a square, the thumb trick doesn't work. Okay? So, we're showing a reason as to why we have that other process. Yeah? But the thumb trick, if you guys notice, the thumb trick, it was all about the zeros of the denominator. Even though the thumb trick doesn't work, there might be a way that in our huge system, the thumb trick simplifies the process. The idea behind it, that whole zeros thing. So check it. I'm going to go ahead and make 1, 2, 3 partial fractions. Why am I making 3? Well, one of them is for the x, one of them is for the x plus 1, and one of them is, for the first time, now that we have a repeated factor, the x plus 1 squared gets his own.
But
What?
I have a question.
Yeah.
Why is there one with the square?
That's a good question. What could have come together? Could this multiply by common denominators to get to be a part of that? Yes. Could this multiply by common denominators to get to be a part of that? Yes. Could this multiply by common denominator to be a part of that? Yes. I could multiply him by x over x, he gets to join in. I can multiply him by x and x plus 1, he gets to join in. I can multiply him times x plus 1 squared. He gets to join in. These are 3 options of fractions that could have combined to be that.
Did you just disregard the x? Yeah. When you divided it. When you have the x plus and then the fraction.
Oh, this is a part of my solution already, so I'm taking the remainder and breaking him down because this has already been broken down.
So you can just forget about that.
So at the end of the day, I'm going to go ahead and solve for what this is and replace it right back there. So it's going to be x plus and then all the pieces. You see it?
Yeah.
And that combined will be this big old mess up in its simplest form. Yeah, good question. So then as I keep on going, this guy, he's a linear factor. He's an A. This guy, he's a linear factor. B. This guy, check it.
C.
He's a linear factor raised to a power, but a linear factor, C.
Wait, so why is he raised to a power?
We just said that.
I wouldn't think
It was okay. She was up here looking at the x plus. Any of these could have multiplied by common denominators to be a part of this final solution. This could be times x plus 1 squared over x plus 1 squared. He gets to be a part. This one could be multiplied by x and x plus 1. He would get to be a part. This guy could multiply by x over x. He would get to be a part. So we have to basically leave room for any possible piece that could have contributed. So, Alec, help me out. We have a lot of division. We don't like it. So what do we do in that?
Yeah, that's what we don't want.
Multiply. Good. Legally though, but yeah. Multiply, yeah? Now pause. We're in honors, not regular. So I'm trying to show you how hopefully your somewhat mental math capabilities can make this simpler for you than that. I'm multiplying by one side and by the other this whole shebang. True? When I multiply by this, isn't he gone and I just get my 5x squared plus 20x plus 6? But when I multiply the a over x times this, who's left when the x reduces away? When I multiply this over here, and one of the x plus 1s reduces, what's left with the b? And when I multiply this over here, and the x plus 1 squared component is gone, what's left with the c? Now, if you didn't follow that, no stress. But those of you that did, start pondering, how could I make something with a's and b's and c's? For the rest of you guys, you could have also just written it out. But when you write it out for one, write it out for all. So you have your x times x plus 1 squared. You would have actually reduced the x and been like, oh, hey. One of the x plus 1s goes away. But 1x and 1x plus 1 remains. And then c is left with 1x. So you can actually write it out if that helps your brain process it. But if you're able to kind of do mental math, basically what's going to happen every time is the numerator will be left with the other parts of the denominator. Why do I need 3 colors and purple and yellow are not enough? Do I still have a constant? Yes. Do I still have an x term? Yes. But why am I coming up to say, oh, crud, I need another random color that's not one of them? Because I also have an x squared term. But wait, how many unknowns do I have? So of course I need 3 equations in order to solve for 3 unknowns. So if I was doing that, now wait a minute, if. When I say if, don't I usually mean there's another way? Okay. If I was doing it, you're okay. If I was doing it the system of equations way, something's going to equal 5, something's going to equal 20, and something's going to equal, 6. Where did my 5 come from?
the extra.
I have some x squared terms. Where's my 20 come from? I have some x terms. And where's my 6 come from? I have some constants. But how do I find them? Well, I gotta multiply all this out. And when I multiply all this out, now I'm gonna go ahead and quickly FOIL this dude, x squared plus 2x plus 1. I I'm going to have an ax squared. Ooh, a is a part of the x squared one. Uh-oh, hold on, there's more. Plus 2ax. Uh-oh, 2a is a part of the x one. Plus a. Well, he's a part of the constant. Then I have bx squared. Oh, wait, that's back to the x squared, right? And then bx. Oh, that's a part of the x one. Oh, and then that's it? And then I just have cx. Oh, that was a part of the... Oh, nice, that's it. Now, you could do color coding. I could have made that guy pink and that guy pink. I could have made this guy purple and that guy purple and that guy purple. And then I only have one that doesn't have an x, so then he's, I guess, the only yellow guy. But I could go through and color code first. I just went straight to making equations. But there's a squared with a squared. Then I have, there's an x term with an x term. It's all about grouping.
Wait a minute, you already have row echelon form.
Well, mostly. Mostly. Actually, wait, why is Alex saying row echelon form? I mean, it's not a gorgeous stair step. It doesn't actually, but what do I have right here? Ah! With an A, can't I mean, we're humans. We're not calculators, right? So can't we be like, we already have A. If we already have A, where can we plug it in to find B?
The A plus B.
The A plus B is 5. So 6 plus B is 5. B must be -1. And then if I have A and B, I can plug and check. Now, I know, guys, we've been doing systems for a few sections. I'm not showing all of my work. But once we have one, we know we can plug in. I could have made it look pretty. Out here, like this would have been on top. This would have been second. That would have been third. But yeah, I can plug and check. 2 times 3 is 8. 6, 12. 20 minus 12 is 8. And then I have a -1. 8 plus 1 is 9. Pretty quickly. Now, this one was nice. If it was mean, I would have had to do my row echelon.
Oh, no.
Well, there's an or, there's an or, there's an or. But now I have Izzy and Emily. See if you realize why I'm writing x plus, yeah? Because of the beginning, it was x plus what? Oh, x plus all my pieces. And my pieces are A, that's 6, over x, plus B, -1, over x. Ugh, what is it, plus 1? Plus 1. Plus C, 9, over x plus 1 squared. And then if you guys ever wanted to check your answer, couldn't you get common denominators, mush it all together, and then see? You could. It would take a lot of work. But you could. But to make you realize, I said that there was an or. So the or starts out the exact same. Where it changes is right here. And it says that thumb trick method has covering factors and plugging in zeros. I can plug in zeros even if it doesn't work quite as nicely as the thumb trick method would say. What are my zeros of my factors? X equals 0 and x equals -1. Now, it's not going to be as simple as if I cover right now, I only find 2, I need 3. The cover-up method actually fails. But I can still plug in the zeros and be like, I wonder what that does. What happens if I plug in 0 anytime I see an x? 0, 0, 6 equals, what's 0 plus 1? Squared times a? What's 0 times anything? Oh, a equals 6! I got it without actually having to multiply out and match it up. Wait a minute. Is this helpful too? Now it's going to be a little bit harder, but what's -1 squared 1 times 5, 5. 20 times -1, 6. Oh, there's a few more numbers, but the nice thing is they all combine to be -9. Double check me, yeah? Now wait, what's -1 plus 1? 0. What's -1 plus 1? 0. Oh my goodness. 0 plus 0 plus c times -1. Hold on. So what does c equal? And what do we do if we have a and c? Once again, I have not multiplied out. I have not made 3 different equations. I do not have a system to solve. I'm just kind of going looking for clues. And if I plug in the zeros, I'm bound to simplify things a little bit. Guys, what do you do if you have a and c? I don't have any more zeros, so now I just get creative. And to get creative, I pick some other random x and say, well, what happens if I plug in? Haven't done 1 yet. 1 is 5. 1 times 20 is 20. 1 plus 1 is 2 squared is 4a. 1b, 1 plus 1 is 2b. 1c, can't I plug in a c, and can't I plug in an a, and can't I solve for b? Now, this is definitely not a very computerish way to go about it. It's not systematic, it's not procedural, it's creative. But it's a way of cheating the system. But it all comes back to, you can use those zeros. Bye, guys. Play with homework. We get to practice a little bit more tomorrow, yeah? This isn't due till Tuesday? Start. Plug in zeros. We'll see where you get stuck. Jaden, go get some fresh air. Take it out.
Jaden, are you okay?
No, I'm sorry.
See you later. Come visit whenever.